Alright, welcome to the second and final half of the final exam review. Let us begin. So we talked about older stuff last time, some stuff that was like on midterm 2 and slightly and was taught around that time, and now we'll talk about newer stuff. So stuff closer to the end of the class. I would like to start with searching. So when you search for something, you're trying to find something inside of a bigger thing, right? You have a vector or you have an array, and you're trying to go through that vector / array, usually, that's the data structure we know about. You're trying to find what you're looking for. Okay, so there's multiple ways of going about it, of finding that thing you're looking for. The first way is the easy way, linear search. Say we have an array. We have to go through it if we're not sure where the thing that we're looking for is, right? So let's get a concrete example. Let's say that we are looking for the number, num to search for is equal to like 3 or something. We're not sure where the 3 is in this array because there is no ordering. The best we can do is just search for it from left to right. So we'll search through all the indices of R, and eventually we'll find our 3 and give back that index. Okay, that's how that works. You also have the potential of not finding the thing you're looking for, right? So let's say that we're looking for the number 42 instead of just a single digit. We'll still go through the entire array. We'll notice that, oh man, it's nowhere. We'll get to the end because we know the size of our array, and we will return -1 when we don't find the thing that we're looking for. Okay? So linear search is the best you can do when you're not sure about the order of things in your array. You have no guarantees about the ordering of things. But that also means that linear search works always. Even if the vector is sorted, you can still use linear search. It's just not as efficient, right? But it'll always find it if it's there, because you're checking every index. Binary search is better though, right? Binary search is when you have the idea of where something is based on the ordering of the elements. So let me sort this array, for example. Let's pretend that we sorted it, so it goes like 0, 3, 5, 6, 7, 8, 9. So that's my array now. Binary search takes advantage of the fact that the array is sorted. And it does this kind of guess the number game on the elements of the array, really on the indices. So because the array is sorted, for example, if I look here at this index and I see 6, I know because the array is sorted that everything to the left is smaller than 6 and everything to the right is greater than 6. Yeah? I know a lot about the array based on that. So we can play that guess the number game where we search first in the middle. We search for what we're looking for in the middle of the array, and depending on where or what's there, if we see a 6 and we're looking for maybe num, maybe num is 8. If I see 6 but I'm looking for 8, I know that that 8 must exist in this half of the array, and so I've cut off the search space, okay? And then I'll keep checking in the middle of that new search space, and then maybe I'll whittle it down to this way, to this way, to this way, blah, 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 if it's a very large array. Eventually, that search space is going to get tiny, because we cut it off by half every time, and either we're going to find what we're looking for in our tiny little search space in the middle of it, or we're not going to find what we're looking for, and we'll return -1. But it's very fast, because it cuts off half the array every time we observe what's in the middle of our search space. Okay? So I'm going to program this up for us. Let me first show you an example of what's going to happen that'll help us when we program this again. Okay? I know I already programmed it for you once, but we'll do it a second time. So let's say that our vector is 2, 4, 6, 8, 10. That is our vector or our array. And let's say that we are searching for the number 2. So the num that we're looking for, num to search for, whatever I called it, That's 2. All right. So the very first thing we do with binary search is we set up some indices, right? We set up some indices. Where could this 2 be? Well, because we have not observed anything in the vector/array yet, the lowest index where 2 could be is index 0, and it really is there, and the highest index where the number 2 could be is 4. That's too large, right? So what we need to do is check the middle of my search space. So I'm going to take low plus high over 2. What's 0 plus 4 over 2? That is the number 2. So the middle of my current search space right here, I'll call mid, is the 6. And so I look at the 6, I see that, and I compare that to the number I'm looking for, to my 2. I see that it's smaller, which means that if the 2 is anywhere in this array, it's to the left. It's over here, okay? So I've just cut off all 3 of these elements, and I can look down along this way, which means I need to change the search space to just include these 2 indices, which means low stays the same, but high kind of switches to be right, to be right there, to be index 1, all right? So that's the next thing that happens. Two, 4, 6, 8, 10, 0, 1, 2, 3, 4. So now low stays here, and high becomes the new, or the new high becomes the old mid minus 1, right? That index. It's definitely not the 6. We already looked at the 6. So it could be between index 0 and index 1. That's my search space. And I'm still looking for 2. And so I'm going to look in the middle of my search space. I'm going to do 0 plus 1 over 2, and that will give me 0 as an index, right? Because we're doing integer division. That'll give me the midpoint is 0, and so I look there, compare it to what I'm looking for, and oh man, yeah, those are equal. Cool. I have found it. Yay. So that is perfect. That's how you search for 2. If, however, I was searching for something that wasn't there, like 1, let's say that I was looking for 1. Everything is going to stay as it was before, but let's pretend in green that I'm looking for 1. So I'm going to observe the 2, notice that my 1 that I'm looking for must be before it, if it exists. So I need to look to the left. There is nothing to the left, right? What that means, though, is that high needs to change when the thing I'm looking for is smaller. So just like it did last time, high needs to become mid minus 1 again. So high is going to be set to -1 now. It's going to pass low. So it's like searching between all the indices from 0 to -1 in that order, which makes no sense at all, right? So when our low and high pointers, high is green, low is still the blue one, when those cross each other, when the indices cross each other, that means the search space is empty, and that means we did not find what we're looking for. Okay? I hope that's all coming back to us now. So that's binary search in a nutshell. Let me implement it for you. Boop. This is the right folder, yeah. So binary search. So let's have our vector. Let's make it a vector, because why not? Two, 4, 6, 8, 10. And let's binary search v for 2. And we'll also binary search v for 1. So it's int binary search because it returns the index where it finds it, if it finds it. Oops. And it takes a vector of ints. We'll take it by reference, const reference, so we can't change it. And then we'll also take what we're looking for. That's what I called it before, val to search for, right? So now, let's do it. I need to start off my search space. So int high, or int low is 0, int high is v.size minus 1. That's the upper and lower indices of everything. And then I need to keep on searching while low is less than or equal to high. While they have not yet passed each other, I have a valid search space. While the search space is still non-empty, let's search. So let's get the midpoint. That's low plus high over 2. And then I am going to look at the value at the midpoint. So if v at mid is, if it's smaller than what I'm looking for example, I need to do something. I need to do something else if v at mid is greater than what I'm looking for. So that's the two cases where where they differ, right? And then finally, the else case, if we get here, we found it. That means v at mid must be equal to the value we're looking for. In that case, the index where it exists is mid. Return mid. All right? In these other cases, we need to change our search space. So let's think about this. So if v at mid, the value that I see, is smaller than the value I'm looking for, that means the value that I'm looking for is in the bigger half of the array, right? It's a bigger value, so I need to look to the right. So that means I need to advance, look in the right half. That means I need to advance my low. I need to change my low pointer, my low index. Low becomes mid plus 1, because we just looked at mid, it wasn't there. It's indices greater than mid. So let's start at mid plus 1, okay? Likewise, this one is look in the left half. If the opposite is true, if the value you're looking for happens to be smaller than the thing you are trying to find, than the thing you see at that index, yeah? That means we need to look in the left half. That means the high needs to change. High equals mid minus 1. It's all opposites like that. So that seems to be pretty good. And if we ever plop out of this while loop, that means low and high have passed each other, right? Based on what I'm looking for here. In that case, we need to return -1. If we end that while loop, that means the search space is empty. So that's binary search, and here's it running. Binary search, binary search. There we go. Index 0 is where the 2 is. -1 is, I guess, where the 1 could be, but if it existed, it is not there. So we say -1. Okay? That's binary search, and those were some examples of it. Let's move on now to recursion. So recursion is all about finding the problem in terms of itself, inside of itself, right? But that inner problem, that sub-problem, better be smaller for some definition of smaller, otherwise you won't ever get to your base case, remember that? And actually stop the recursion, the looping, right? The looping using stack frames. So let's do my 2 examples that I have planned here. Let's do example 1, calculate x to the power of n. So given any number, I claim that taking it to some integer power is a recursive problem. So what is x to the 5th but x times x times x times x times x? And here is a smaller something to the power of something problem. That's x to the 4th. You see that? So if we were to generalize this into a recursive case rule, we would say that, okay, instead of x to the 5, let's say x to some n, some integer n power, is equal to x times x to the n minus 1. See that? That's how it breaks down into a smaller subproblem. So that would be where our recursive call goes. And then we need to think about what's the smallest number to an integer power that I can just immediately give back an answer for. And so if you unfold this, you try this out for x to the 5th using this recursive rule, eventually you'll notice that the place you want to stop is either x to the 1st, which is defined to be x, or you can actually go one further than that. You can just say x to the 0th power, define that to be 1. If you ever see the power you're taking a number to is 0, just immediately give back 1. Nothing else to look at, right? That's a stopping condition. So with that, that's another way to make it work. That is a recursive algorithm. So cout, I don't know, I'll call it pow, to the 5, for example. And so this is a recursive function, I'll call it pow, and pow xn, right? So this returns x to the power of n, and we have to figure out as usual, if we're in our base case or our recursive case. So if n is equal to 0, return 1, else we're in the recursive case and we need to return x times x to the n minus 1 power. X times, what is x to the n minus 1? Well, it's a call to ourselves, x and n minus 1. Isn't that neat? So that's how that's working, and that is our recursive algorithm. And so this will eventually get down to the right answer and give back the correct solution. And so 2, 4, 6, 8, no, 2, 4, 8, 16, 32, yeah, 2 to the 5th is in fact 32. Awesome. And if you're having trouble with recursion, I have made a nice little page here going through an example of breaking down a recursive problem, doing just what we did for the power problem, but this time for factorial. You remember that? That's the first one I taught you. So the best way to come up with a recursive solution is to write out some example. So like, what's your problem to some number? So that p of 5, for example, if it's factorial, is, well, 5 times 4 times 3 times 2 times 1. Then you find the problem inside of itself. There's the next smaller problem. And then you can come up with a generalized rule, right? A recursive rule. So here's that generalized rule. And you get to assume that the recursive call always works due to the magic of recursion. Like, I'm assuming this is going to correctly calculate x to the n minus 1th power. And I can just take that on faith. And as long as I build up the answer for the final solution, the original question, correctly, it really will work, which is really cool to think about. That is the magic of recursion. And then we also need to find that stopping condition. When is there an answer we can immediately give back? And yeah, you just rinse and repeat until you have some equations that look like this, and then you turn them into code. Okay, so that's recursion in a nutshell. So let's go back to here. That was my first example. My second example is one that I haven't done already in class. Let's do a recursive binary search. Okay? The way you can make binary search recursive, well, we have to think about what is getting smaller, right? What's getting smaller? The answer is the search space. Right? As you progress through binary search, the thing that's getting smaller is the distance between your low and high. So that is key, okay? The search space is the thing that's getting smaller. And so we need some extra parameters to keep track of the search space in a call to binary search, because that's what needs to get smaller, right? The distance between low and high. And so that is how we're going to call binary search. It's still got to take the vector, the thing we're looking for, but it will also take low and high, those initial, those indices of that represent my search space. Okay? And so this will make sense once I code it up, but we're going to just immediately give back the result of calling ourselves with a smaller search space. So let me show this to you. This is really cool how we're going to change this. So let's take the stuff we had before and we'll translate it into recursion. Okay? So here's the idea. Let's make this recursive binary search. And so a lot of this is going to get rid of itself. No more loops necessary, but we're going to have a base case and a recursive case. Okay? Maybe we can do the recursive case first. So I am going to take low and high as parameters, and so the way that I call binary search is then I start it off like this. Like low always starts at 0, the search space is the whole thing, and then v.size minus 1 is high. So those are my parameters. Now that's how I'm going to call binary search. And now let me show you the recursive case, for example. So in the recursive case, I have to keep looking at smaller things, yeah? So I look at my midpoint between low and high. I was given low and high, the parameters now. I don't need a loop for this. And then I check, like, is v at mid less than val to search for? If so, I need to look in the right half. Is v at mid greater than val to search for? If so, look in the left half. Otherwise, if we found it, we really can return the answer. That's fine. Return mid there. That's totally okay. But these lines right here, low equals mid plus 1 and high equals mid minus 1, those need to become recursive calls, right? What is look in the right half but binary search in the right half, right? That is binary search in the right half. So I have a function for that, right? Call ourselves. So the result is, if we go down this half, the result is binary search on V for the same value, but we're looking in the right half, which means that low becomes mid plus 1. You see, that's the parameter position for low, and high stays the same. So this is going to go off and search in the right half with a smaller search space. Do you see that? That's the key. And then it's going to return back the answer. Either it's going to find it and return the index, or it's not going to find it and return -1. Whatever the answer is, that's the answer for the whole thing. So I'm going to return that result. That is what's happening here. All right? Same game here. So for this game, we're looking in the left half, so low stays the same, but high becomes mid minus 1 for our next round of searching. Okay? So binary search in the right half, so call ourselves on a smaller search space. Whatever we give back is the answer, right? It's either -1 if we didn't find it, or an index if we did find it. So that is the recursive case. So please yell at me if that did not make enough sense. That is how I want you to think about it. All right, this is a slightly more complicated example though. So that's the recursive case. The base case is, well, when are we done? When is there nothing to search through? Well, that's when the search space is empty, right? That's kind of like the loop stopping condition right here. That's essentially the idea. So if the search space is empty, that means low is greater than high, right? That's the opposite of this, right? Low less than or equal to high. The opposite of that is low is greater than high, right? If that's true, we're done. The search space is empty. Return -1. Otherwise, we're in the recursive case. And we do all this. Okay? That is the idea. And so we're always returning some result, but we might have to throw the problem off to ourselves, a smaller version of ourselves. So that is the full binary search algorithm there, made to be recursive. And still, we get the correct answer. So searching for 2 in 2, 4, 6, 8, 10 really is at index 0, and then 1 is not there, so it's -1. We're getting down to the base case. So isn't that fun? That is recursion. All right. So let's see. The next thing that I want to show you and talk about is Makefiles. So let's go back. Let's go back and talk about just compilation in general first. So what is compilation? We have a compiler, right? We have a compiler and we also have a linker. They do slightly different things. So the compiler is G++, but a compiler takes a single source file, a single .cpp file, and turns it into machine code. Okay? So G++-C, that's the compiler part of G++. And it creates the .o files. That's the object code. Okay? That's what we need to remember. Only once we have a bunch of object files for individual C++ files can we combine them all using a linker. We also might have some pre-compiled stuff like IOStream. We might have vector, all these libraries we need to include and link together in a final executable program that we can go and run. Okay? The linker does that. It takes care of making a final executable program. Okay? And we would like to have control over this. We'd like to have control over going down to the .o file stage for every individual file, because that is called separate compilation. It makes everything very quick so that we only have to recompile what's changed. Okay? Remember all this? So that's what we'd like, and Makefiles are a nice way of specifying all of this. Okay? A nice way of specifying all of this stuff. And so the final thing that you can go and run with the // recursion or whatever. that's what we want to get towards by linking a bunch of .o files and also our libraries. Okay. Unfortunately, the linker is also called G++. You just give it the .o files instead. Okay. But let's go now to a Makefile, and that will tell G++ exactly how to go and build everything. Okay, so let's remember how all the terminology. You got your targets, that's what you want. You got your requirements, what you need in order to make your target, and then you have the body of the rule. You tab over and you say all the terminal commands that are going to go and make that target using the requirements. Okay, so I guess my fun example for us is let's make a recursion library. So let's separate out our main function, all of our recursive functions, and let's make a recursion library using this idea of separate compilation, and we'll compile them all with a Makefile, the whole bundle. All right. So also here on this page, I guess it's a bit out of order, I have information about Makefiles. So let's remember all of that. So let's pretend here that we have 3 files that we want to compile. And remember that we're never going to give .h files to G++. It's only implementation files. All right, so here's what the Makefile looks like. And remember, it's a file called exactly Makefile. Here's the Makefile language. All right, the target is the thing before the colon. You can have as many targets as you need, a bunch of different rules in a Makefile. All right, so here's the first rule. It is the rule for making a.o. Okay, and then the requirements are the things that come after the colon on the first line. So there's only one requirement to make a.o. It's apparently a.cpp. All right. They can be space separated if you have multiple. And then you tab over and you say exactly how to go about using the things that you have in order to make your target, the thing you're looking for. Okay. And so you can make a.o, you can make b.o in the same way, and then you can link them together in this final rule to make something called prog. Okay, so it requires a.o and b.o, and here's how it links them together to make the final program exactly called prog. Yeah, so that is what we're looking for. And Makefiles are beautiful because you can just be like, hey, I want to make prog, and it'll go and make a.o and b.o using these rules if they do not already exist. It's great. Okay, so let's use this kind of pattern. Let's remember everything, and let's do it for our recursion stuff that we just wrote. Okay. So I have recursion.cpp. Let's also make recursion.h. Let's remember our header file guards here to protect against infinite inclusion. But my recursive functions are pow and binary search. So let's declare them here. And I'm using vectors, so I need to include vector. And because this is a header file and it gets copied and pasted places, I do not want to say using namespace standard. So anything from the standard library better have a standard : out in front of it. All right. So those are my declarations of the functions in this library. And then here I will implement those things. So I guess I don't need this right now. I guess I do need using namespace standard. I'll also include, it's customary to do that, include your header file. And then here are the 2 implementations of the things, there we go, of the things in the header file. You got your pow, you got your binary search. The rest can go in a third file. I'll call it like main.cpp. That holds the main function. So I'll take all this. Boop. And this will, again, include our library. And then do stuff with it. So here is a use of the library. Here are 2 uses of the library functions. All right, so I've just made these 3 files. I've made recursion.h, declaration of the library functions, recursion.cpp, implementation of those 2 library functions, and then main.cpp, which includes the library and uses it. Okay, so now I'd like to compile all 3 together. And the goal is to go through .o files. So here's what I would like to do. I got my recursion.cpp, and I got my main.cpp. Those are the 2 files, the 2 implementation files that need to be compiled. I will compile them. I will compile them into recursion.o, and main.o. So that's machine code for just those individual files, and then I will link them together with the standard library stuff like IOStream and vectors, and that will make a final program that I think I'll just call main, that I can then go and run. Okay? So that's what I want to go through. Make the .o files, make the final thing. Okay? So let's make the makefile. It's a file called exactly makefile, and there are 3 rules, right? Because I need to know how to make 3 things. This .o file, this one, and the final executable. Okay? So recursion.o, if I want to make that, I need recursion.cpp, right? That's my requirement. That's what I'm making recursion.o out of. And then I'm going to go and compile it. -c recursion.cpp. That will make recursion.o. Then I can do the same for main.o. It needs main.cpp. And then finally, I can do main, the final program. I need to link together main.o and recursion.o, so I better have both of those. If I don't, go and make them. And then to compile, I give them all. I give all my .o files, and I output a final executable file that I've linked together called main, right? So that's why I say -o main. And so these are my 3 rules. And now I can compile with, I can say make recursion.o if I'd like to. That makes just a single thing using that rule. Or I could say, let me actually remove that. Remove recursion.o, so blank slate again. Let's say make main. Oh, oops. It looks like I did something wrong here. Yes. I copied and pasted this wrong. To make main.o, I need to compile main.cpp. Oops. So let me remove all the .o files again. And now let's try it once and for all. Make main. It notices that it still needs main.o and recursion.o, so it goes and makes those first, running those rules. And then finally, it has those things and can go and run the body of the original rule to make main the executable file. But here are the .o intermediate files. Okay? I can say /main, and bam, still runs, still works perfectly. One nice thing about Makefiles is the first rule gets run when you just say make by itself. So usually you place the most interesting rule up top, and you can just say make, and it'll make it for you. So that will now default to main, because that's the first rule. And the beauty of Makefiles is they notice, based on these requirements, what has changed. And so they only recompile what needs to be recompiled. So for example, if I change this and I add another call to binary search, let's look for the number 8 this time. If I make it, it notices that it only needs to remake main.o, right? It can link with the same old recursion.o because I haven't changed recursion.cpp. And so, there's the new addition. Everything works as it should. Yay. So that is Makefiles. Let's keep on trucking. Let's move on to Bitwise Operations. So, remember those, we're acting on the individual bits of a number, usually ints. So don't forget that ints are 32 bits long, and here's an example int 1011 ... 0011. Don't forget that the numbers of the bits are like this. The 0th bit is over here. Here's the bit number 1, bit number 2, bit number 3, all the way to bit 30 to bit 31, right? There's 32 total, so if it starts at 0, the last one is 31, not 32. And so bitwise operations are all about extracting, doing stuff with individual bits of a number. So it performs usually logical operations like and or and stuff on those bits of usually 2 numbers. So for example, I can bitwise and together 2 numbers. I can bitwise or together 2 numbers, or XOR. Bitwise not only takes 1, right? So let's remember all this stuff. So in general, and is good for checking bits. Remember that? So here's my number. Let's say I want to check if this bit number 2 is set. I can AND with the special number that has a 1 right there and a 0 everywhere else, so that it picks out this bit if it's there, and it's a 0 if it's not there. And so if this result is non-zero, that means that bit really was set. Okay? So that's AND. It's good for checking bits. OR is good for setting bits. You OR a number with another number, you'll end up having that thing be a 1 in the proper location. XOR is good for flipping bits. Remember that? Because if you have 0 XORed with 1, it makes it 1. And then if you have 1 XORed with 1, it makes it 0. So you just XOR with a 1 in the right position and it toggles it. That's cool. There's definitely more that you can do. There's also shifts, and I'll get into that in my example. Okay? So let's see. What do I want to do? Let's have these two examples, and that will hopefully explain a lot of stuff. So first of all, here are a bunch of examples of all those bitwise operations. Hopefully that helps you as you're studying for the final. And these are all those operations doing cool stuff. Please yell at me if you have questions about it. But let's make two examples. Let's make a multiply by 2 to the n function that takes a number and multiplies it by 2 to the n using bitwise operations. And then I'll also make a flip bit function that takes a number and flips that bit in that location. Alright? So that's what I'd like to do here. So for example, let's do multiply by 2 to the n first. So I think I'm going to need to return values each time. So return an int, because we're given an int. And it looks like some weird characters have appeared because I copied and pasted from a PowerPoint. Now it's looking better. So this is going to take a number x and a power n, and this should return x times 2 to the nth power. That's what we'd like to do. And so we're going to use bitwise operations to get us there. So for example, if x is 3 and n is 4, that means I would like to do 3 times 2 to the 4th. Yeah? Which is 3 times 2, 4, 8, 16, which is apparently 48. I did that ahead of time. And so the question is, how do I easily do that? Right? How do I make 48? And what we need to do is notice that shifting is the right answer here. Remember that? So we start with our number 3. So here's 3, 1, 1 in binary. If I shift that left, base 2, if I shift that left by 1 bit, that creates 1, 1, 0, right? Which is really 6. Okay. 1, 1, 0 base 2, which is 6. And that means this left shift by 1 really multiplied by 2, right? It's really multiplying by 2. 2 to the 1, actually. If I do the same thing, 1, 1, 3, base 2, shifted left by 2 bits this time, that makes the binary number 1, 1, 0, 0, 2 zeros at the end, which is equal to 12. Okay, you see the pattern? This is times 2 squared. So the thing that you want to multiply, your power against 2, is always the number of bits you're shifting to the left by. So if you want to multiply by 2 to the 1, shift left by 1. If you want to multiply by 2 squared, shift left by 2. If you want to multiply by 2 to the n, shift left by n. And so we get our 48. Very nice. Alright, that's the first example. Next example, let's do flip bit. So that's going to take a number, and it's going to flip the bit of that number. So let's say, for example, that our number x that we want to flip a bit of is, I don't know, 1101. And let's say that I would like to flip bit number 1 of this number. So that means I need to flip this bit right here to a 1, and XOR is good for that. So I'm going to XOR by a 1 in that position and a 0 everywhere else. And that's going to flip that bit while retaining everything else, right? So now it'll be a 1. Nice. So that got flipped. And then if I take this one, I do the same thing. It toggles it. It really does. If it was a 0, it makes it a 1. If it's a 1, it makes it a 0. If I flip this bit again, I again XOR by just a bit right there in position number 1. So this retains everything else due to the way that XOR works. And then because they agree, XOR is like, no, false. And so that is how you can flip some bits. All right, so you always XOR by a number with a 1 in the position that you care about for that bit, and a 0 everywhere else. All right, so what is this number but the number 1 left shifted by 1? So it's always 1, and then you left shift it by which bit do you want, right? So I want bit number 1, so I'm going to left shift it by 1. I hope that makes sense. So, I don't know, cout flip bit. I want to start with this number. I want to start with this one down here. This is 1, 2, 4, 8, so 8, 12, 13. So this is the number 13. I want to flip bit 1 of 13, and that should apparently make this one, which is 15. So I should see 15, and then 15, flipping the 1, bit number 1, should make 13 again. All right? So it should subtract 2. That's the idea. It gets rid of the 1 in that place, which contributes 2 to the binary number. So that's what I want to have happen. And so here's what I do. I return x XORed by the number where there's a 1 in that position that I want to flip, in the bit position where I want to flip, and a 0 everywhere else. And so it's take a 1, shift it left by that bit I care about. And so I see my 15 and my 13. Very nice. All right. So those are bitwise operations. Again, please yell at me if you have any more questions about things. Also study this. And then the final thing that I want to talk about is exceptions. So exceptions are for telling the user of maybe your library that something went wrong. You used my library incorrectly. Okay, so you throw exceptions, and somebody else, it's their job to catch them. Okay, so you throw like a runtime error, and runtime errors take a parameter that is a string describing what went wrong. Okay, and those live in standard except, but the standard pattern is, well, you try to do something, you try to do some code that might throw an exception, and then you have to catch each exception that could have been thrown by that code. All right, you catch it by reference. Okay, so if you forget to catch a particular kind of exception and it really ends up happening, if it ends up getting thrown in the program will end with a runtime error. Okay, but you can recover if you catch it. That's the beauty of it. All right, so let us have this first example. Let's make a recursive power function, kind of like the one we have, but let's have it throw a runtime error when it's given a negative argument, because it won't work like that. It won't work properly. It would have like an infinite loop if you were to give it that, because the recursive rule would always apply. It would never get down to the base case because it was too low. So let's fix that by throwing a runtime error if that ever happens. And so I'll show you how to do that. And let's also go back to the examples here. So this is kind of how it's going to work. You try to do something that might have an exception, you catch those things, maybe multiple different kinds of things, and that's how that works. But it's somebody else who's throwing it. It makes no sense to put a try-catch next to a throw. It has to be somewhere else. You hand off the problem to somebody else. Okay, so let's steal a lot of code. So let's steal this POW function. Oops. There we go. And let's steal the flip bit function. Boop. Okay. So first issue, I would like to throw an error if we try to calculate the power where the power is negative. So try to do 2 to the negative third power or something silly. This should never work because we'll never hit the base case. It'll be an infinite loop. It'll always go here, which is no fun. So that's the first thing I want to deal with. And the other thing that I'd like to deal with is let's throw an exception if we're asking to flip an invalid bit. So for example, it's okay to flip bit 1 of the number 13, but it's totally not okay to try and flip bit 33 of the number 13. That bit totally doesn't exist, right? So we should throw an exception in that case. So let's include standard except and use one of the standard except library exceptions. So if n is less than 0, then throw a runtime error. And here is, like, we can say can't use negative powers. And so that'll be the runtime error there. And then for flip bit, if which bit is invalid, like it's less than 0 or it's greater than 31, then let's also throw an exception. Okay, so that's how we can throw exceptions, and the idea is we pass off the problem to somebody else. So 2 to the third power, the normal third power, works just fine, but 2 to the negative 3 will not work. That'll throw the exception, and so let's catch it by reference. And so runtime errors have a .what method inside of them, and that just gets out the string that you put into it. The string. So that's what it'll give back. And so we'll just output that. Okay. We'll do the same for these flip bits. So try to do all this stuff, but we could again throw a runtime error. So let's catch that. And you can throw any type, by the way. I could throw a string right now. I could throw the string invalid bit. And actually, let me do that. It's totally fine to throw anything, okay? And so here, let's throw a string. Okay. That'll work. And so in this case, we need to catch a string, because that's what's being thrown. And I guess I'll call it S. Okay? So no matter what type of thing got thrown to us, we better catch it, handle it. We'll just print out the thing. That's how we handle our exception, and call it a day. So that's exceptions. Yay! So it works when it can, but the second an exception occurs, we jump to the corresponding catch block, and we handle that exception by, in our case, just printing stuff out. So again, try these. The first one's fine. The second one fails, though, with an exception. We catch that exception and recover from it, and so the program's fine. If we do not recover, right, let me put this outside. If we don't recover, then we get a runtime error because you didn't catch that exception. But as long as you catch them, the program will continue and execute as normal. So that is exceptions in a nutshell. Yeah, so please yell at me if you have any questions about that. And that, my friends, is the review. That is everything that I have planned for you. So that brings us, therefore, to the end of this class. This was the very last lecture. Yay. So you made it. Thank you for putting up with me this whole semester. And please enjoy these memes on the very last slide on the last day of class. So good luck on the final. Please yell at me if you have any questions about anything. And I will see you in office hours or perhaps on the day of the final. So yeah, see you then.